Modern software engineering is constantly fighting a war against entropy. Every time you deploy a new application, you create a new attack vector, a new state to manage, and a new stream of decentralized network traffic to monitor. Today, we are looking at a specific, highly common engineering challenge, taking an existing ecosystem of 18 independent applications and migrating them into a single, unified identity architecture. This diagram shows the typical starting point for a fragmented ecosystem. We have 18 application server nodes, and each one is physically coupled to its own isolated user database. Every app maintains its own local session state, its own password hashing, and its own discrete login infrastructure. When a user updates their password on app number 3, app number 7 remains entirely unaware. Multiply this redundant password storage and duplicated multi-factor authentication logic across 18 nodes, and you generate severe synchronization failures and drastically expand your attack surfaces across the network. Having users log in 18 separate times is undeniably a poor experience, but the real issue is that maintaining fragmented authentication logic physically prevents you from scaling your infrastructure securely. To fix this, we need to build an internal system that mimics the exact functionality and security posture of enterprise identity providers like Microsoft Entra or Google. The local session management currently sitting on each server must be stripped away. As shown here, we are collapsing those isolated databases and rerouting all traffic to a single centralized source of identity truth. This central hub operates as your authorization server. It is an OpenID provider tasked exclusively with user verification and session management for the entire ecosystem. This shift demotes the 18 applications. They are no longer responsible for user credentials. They are now categorized strictly as relying parties or clients, and they are required to communicate with the central server via standardized protocols, OAuth 2.0 and OpenID Connect. Consolidating your ecosystem requires completely removing user verification logic from the application layer and handing it over to this dedicated identity engine. The authorization server itself is not a monolith. To function securely, it must be subdivided into distinct logical engines responsible for consent, data storage, and cryptography. The authorization server acts as a core routing engine. It receives credential requests, generates consent screens, and orchestrates data flow to 2 subcomponents. The first branch leads to the identity store, a highly secured database strictly housing encrypted credentials, profile metadata, and passwordless authentication keys. During multi-factor authentication, validation executes entirely within the identity store. Downstream applications remain completely blind to the MFA event. The second branch is the token service, the server's cryptographic engine, responsible for generating, signing, and issuing JSON Web Tokens. Separating the user database from the cryptographic token issuer ensures that a vulnerability in your application layer cannot be leveraged to dump raw credentials. It isolates your attack vectors and drastically simplifies your compliance auditing. To securely link the applications to the authorization server, we need to establish the precise network routing sequence. The industry standard for this is the authorization code flow with PKCE. This swim lane plots 3 entities: browser, relying party, and authorization server. The app registers to receive a client ID and secret. Unauthenticated users are redirected from the app directly to the auth server's login. This password exchange cleanly bypasses the originating app's backend. By enforcing a rigid browser redirect, you permanently block the individual applications from ever seeing or logging the user's raw password. Once the user successfully authenticates, the authorization server triggers a callback. It redirects the browser back to the original application, delivering a specific data packet called an authorization code. This code is not a persistent user session. It is simply a temporary, single-use string confirming that a login event occurred. Because this code travels through the vulnerable browser, we implement PKCE, Proof Key for Code Exchange. If a malicious script intercepts the temporary code, they mathematically cannot use it. The backend executes a secure server-to-server request, trading the code for 2 newly minted token assets. The first is the ID token, which contains the user's verifiable profile metadata. The second is the access token, which provides the authorization scopes required to access specific downstream APIs. This entire routing sequence definitively separates the act of verifying a user's identity from the act of granting them permissions. It anchors your security in mathematically verifiable tokens, rather than fragile, stateful sessions. Building an identity provider requires a decision on execution strategy. Attempting to code custom authentication architecture from scratch introduces extreme engineering liability. Managing identity means absorbing the responsibility for the OWASP top 10 vulnerabilities, navigating strict GDPR data handling requirements, and continuously passing SOC 2 audits. Most development teams simply do not have the specialized security bandwidth for this. The definitive strategy eliminates custom implementations. Your integration roadmap: adopt an existing framework, define metadata endpoints, manage tokens, and build a developer dashboard. To handle the OpenID Connect protocol logic, you should immediately adopt battle-tested open-source frameworks like Keycloak or Hydra, or utilize managed platforms like Auth0. An engineering team's complexity budget is finite. It must be spent on connecting the unique business logic of your 18 apps, never on trying to invent and maintain custom cryptographic protocols. Once you deploy your chosen framework, you have to correctly configure the metadata to connect those 18 client apps to the new central server. Publishing an OpenID configuration JSON file at a known endpoint lets your authorization server continuously broadcast its capabilities. This allows the 18 apps to automatically configure local libraries without hard-coding URLs. The system routes them directly to the JSON Web Key Set. The JWKS is a directory of public keys. It is the critical cryptographic infrastructure required for managing the lifecycle of your tokens. When an application receives a token, it queries this public key directory to mathematically verify the token service's signature. This proves the token is authentic, allowing the app to grant user access locally without constantly pinging the central database. By deploying standardized metadata endpoints, you transform what could be a chaotic, manual multi-app integration into an automated, highly efficient, and self-healing network. The final requirement in modernizing this architecture is opening it up so external third-party companies can authenticate their users against your system. Built on standard protocols, external partner servers connect to the exact same authorization server hub. Through your developer experience dashboard, you generate new client IDs and map their external redirect URIs, exactly as you did internally. This reveals the true efficiency of standardizing on OpenID Connect. A legacy internal application and a brand new external platform share the exact same integration pathway. Standardizing your authentication logic replaces those redundant data silos with a centralized, highly and cryptographically secure token issuing engine. Look at the current state of your own network infrastructure. If your engineering cycles are consumed by fragmented technical debt, it is time to stop patching databases and implement a centralized OpenID architecture.